Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosine River College in Sacramento, California. This video is a continuation of an introduction to evaluating or working with inverse trig functions. You should have watched my introduction to them in the previous video, because that's going to be critical for us as we move forward, that you know the domains and ranges of all of the inverse trig functions. In this video, we're going to evaluate inverse trig functions, and this usually I would not show an how-to, especially when we're learning something. Usually I like to sort of derive the ideas and really give a natural understanding of how things are working when you evaluate something. However, with inverse trig functions, I've seen so many mistakes over the years that it's probably better for me to just clearly define the steps, kind of how you would attack evaluating an inverse trig function. So in my notation here, you'll notice that I'm supposing that you're being given a trig function that is an inverse trig function. So it could be a sine inverse, a cosine inverse, a secant inverse, a cosecant inverse, something like that. And the argument for that, which is a ratio, we mentioned it last time, but it's probably best to say it again, that this is a ratio. Let me highlight it and point an arrow at it. That is a ratio, not an angle. Okay, so we evaluate inverse trig functions at ratios. And if you're asked to do that, the first thing you're going to do is let theta, which will stand for an angle, let me use yellow for that. So that is going to be an angle. We are going to let theta equal the inverse trig function of y. And again, y is a ratio. That's just something to be very critical about. I really want you to truthfully understand that. I think I made a big stink about it in the last video, but still important. Next thing you're going to do after, that's a very simple step. Just let theta equal the inverse trig function. The next one is you're going to state the restrictions on theta using both an inequality and quadrants. And this comes from the definition of the inverse trig functions. And while it looks like an absolute mess, this is what I had in the previous video. Sine inverse, it returns an angle that is between negative pi over 2 and positive pi over 2. And then you would also state, for example, if you're working with the sine inverse, oh, that means we have an angle in quadrant 1 or quadrant 4. The reason why I insist that you do both the inequality and the quadrants is because there are an infinite number of angles actually that land in quadrant 4. And they, even if they have the same reference angle, there's still an infinite number of angles with that reference angle that land in quadrant 4. However, we are severely restricted. The angle we are going to be talking about must be between negative pi over 2 and positive pi over 2. So not only does it have to be in quadrants 1 and 4, but it also has to be a small angle. And you'll do that with each of these. The cosine inverse returns an angle between 0 and pi, and that's quadrants 1 and 2, and so on and so forth down the line. Once you've done that, you then focus on the argument, that value of y, that ratio that you've been handed. So you're going to focus on that for a moment. If it's a special ratio, like a 1/2 or a square root of 3 or root 3 over 2, something like that, then draw out a special triangle to find theta hat. This is to find the reference angle. And as I've mentioned repeatedly, trigonometry really boils down to two things: reference angles and quadrants. And so in this step, you're finding the reference angles, the reference angle step. If it's not a special ratio, so again, we're talking about that value of y. Let me get a good highlighter in here. Right there. So if that value of y, which is the argument of your inverse trig function, if that's not a special ratio, then it's one of two things. Either it's quadrantal ratio, which would be a -1, a 1, or a 0. And that just means the angle that is going to be spit out by that inverse trig function is a quadrantal angle. In other words, it's an angle that lands on a quadrant. And the easiest way to attack that is just to graph the related trigonometric function. So if you're taking the inverse sine, graph the sine and find out when its output is 1, -1, or 0, whichever your ratio is. We'll see examples of each of these. And then finally, if your argument for the inverse trig function is not a special ratio, nor is it a quadrantal ratio, -1, 1, or 0, then it must be some type of decimal or something like that. Some ratio that is not familiar to you, 0.815 or something like that. And we've never seen that as an output for a trig function, so we have to do something else to evaluate that. You're going to use a calculator. And to do that, you're going to find the reference angle. So again, this is pretty much all about reference angles in this step. You're going to find the reference angle by grabbing a calculator and computing the inverse trig function value of the absolute value of that y. And we'll talk about that when we get there, but that's a critical step. And so you can see parts A and C there are both finding the reference angle. So if the angle is not a quadrantal angle, in other words, your output, your argument for the inverse trig function is not 1, -1, or 0, then you'll use the quadrant from step 2 and the reference angle from step 3 to actually state what the real angle is. Now that seems like a lot, and that's why I don't like to write down how-tos like this, because it really does seem like quite a bit to digest. It's actually a lot easier to just dive right into it. So that's what we're going to do right now. And for each of these examples, you'll note that at the very top it says evaluation of trig functions for non-axial or non-quadrantal angles boils down to two things: reference angles and quadrants. So here we go. Evaluate the expression without using a calculator. Your answer should be in radians. We want to know, what is the sine inverse of √3/2? Well, the first thing I'm going to do is let theta equal that. So I'll just say this is equal to theta. And the reason why I do this is to remind myself that this is going to return an angle. That is critically important. The next thing I'm going to do is go ahead and mention again for myself what are the restrictions on theta. Well, I know that since we're dealing with the sine inverse, theta must be between -π/2 and +π/2. That is, it's going to be in quadrants 1 or quadrant 4. And you could see that if you drew out your kind of quadrants there, you can see -π/2 to π/2 is quadrants 4 and 1. You don't have to draw that, I'm just drawing that. So those are the first two steps, very fast. Just let theta equal the inverse trig function. It's very important there. State the restrictions on theta. The next thing I'm going to do is focus in on that ratio. That is a special ratio. We've seen that before. So I'm going to write special ratio here. And this means I'm going to go ahead and draw a triangle. My π/6, π/3 right angle triangle. π/6, π/3. It's 1, 2, √3. That's the relationship. And now we just need the sine of whatever angle it is to be √3/2. So let me say that again. We need, and I'll actually just pause this and write it down, the sine of theta hat to be √3/2. Notice I put theta hat there. It means I need my reference angle. I need to find a reference angle. This whole step right here is about finding reference angles, not the exact angle, but the reference angle. So this is like the, I suppose you'd call this the quadrant step. And now we're at the reference angle step. Again, trig is pretty much about quadrants and reference angles. And if you look at this triangle, sine is opposite over hypotenuse. So opposite should be root 3. Hypotenuse should be 2. So root 3 over 2 gives me that my reference angle, theta hat, is going to be pi over 3. I almost said root 3 over 2. So I have quadrants and reference angles. Now I will just focus in on which of these two quadrants I'm going to land in. And I suppose I could have been more wordy with my instructions here on the last part, saying if the angle is not quadrantal, which it's not, use the quadrant and the reference angle to state theta. I could have been a little bit more wordy there and just had said, okay, so now consider the fact that this ratio is positive. Well, the fact that this, when I say this, I should highlight it so that you know what I'm looking at. This ratio right here is positive. And so we want to know, of those two quadrants, which is the quadrant where our ratio, our sign, is going to be positive. So let me write that down. Since we need sine of theta to be a positive root 3 over 2, we need a quadrant where sine is positive. Now, of the only two quadrants we're working with, quadrants 1 and quadrant 4, sine is positive in quadrant 1, not 4. And we have a reference angle of pi over 3. So we now know our quadrant. We now know our reference angle. So let's go ahead and state our real angle. If you need to see a picture of it, it looks like this. We are opening an angle into quadrant 1, because that's the quadrant we have, and its reference angle will be pi over 3. Something like this. It's supposed to be a little bit more straight than that, but whatever. So the actual angle is an actual pi over 3. That implies theta, which by the way is sine inverse of root 3 over 2, is going to be pi over 3. Now, as written, that seems like a long-winded way to do something that could have taken only a moment to do. But I'm trying to show you something that will work in all situations, not just one situation. So let's repeat this process. I'm actually going to, maybe I'll just make an example right down below. Let's just make one up. Because the next one is not going to be as instructive as this one. So let's go ahead and try a different one. I'll say, what about, let's do something with a negative angle or a negative ratio. So what about the arc cos, which is, I'm using that notation just to kind of make sure that you're used to the fact that the inverse trig functions have two notations, arc and then the inverse notation. They mean the same thing. So arc cos, which we would say is the arc cosine, of negative root 3 over 2 is the same thing as saying cosine inverse of negative root 3 over 2. They're the same thing. Okay. So what about that? Well, the first thing I'm going to do is just remind myself that the cosine inverse, just like any inverse trig function, is going to return an angle. And then I'm going to state again for myself what quadrants that angle has to be in. So this is my quadrant step where I just worry about what are my options for quadrants. Well, I happen to know that theta must be between, for the inverse cosine, it has to be between 0 and pi, which means that we're working in quadrants 1 and 2. Now again, I highly recommend that you write down both the inequality here and the quadrants, because with a reference angle of, for example, in our last problem, we had a reference angle of pi over 3. There are an infinite number of angles that land in quadrant 1 with a reference angle of pi over 3. The way we knew the actual angle was pi over 3 was the fact that we cannot, the sine inverse could not return an angle outside of negative pi over 2 to positive pi over 2. So that really kept us restricted down as far as what our answers could be. Anyhow, so it is kind of important to write down that inequality. Now that we've written down the quadrants and the inequality, we're going to look at the ratio itself. And the ratio, I'm going to ignore the negative in there. I'm just looking at the ratio, the absolute value of the ratio. And I notice that that is definitely a special ratio. It's from a special triangle. So I'm going to highlight that without highlighting the negative because I don't really care about that. And I happen to know that's a special ratio. And so I reference a special triangle, which I have up above actually, right there. Yeah, right there. And I need, in this special triangle, I need the cosine of my reference angle to be a root 3 over 2. So again, I'm going to write that down. I need, under the reference angle step, reference angle. Since the cosine inverse of negative root 3 over 2 is equal to theta, I need the cosine of theta hat, the reference angle, to equal a positive root 3 over 2. The reference angle is always between 0 and 90 degrees, or between 0 and pi over 2 radians. So it's just a small positive angle is all that the reference angle is ever going to be. If we go up to that special triangle up above, all the way up here, I need to find the cosine of an angle such that that cosine will be root 3 over 2. Now remember, cosine is adjacent over hypotenuse. So the reference angle is pi over 6 because the cosine of pi over 6 is root 3 over 2. So I'll scroll down here and I will fill that in. So this implies theta hat, the reference angle, is pi over 6. So now I'm going to highlight the important pieces here. I have the quadrant, or the quadrants, the choices of quadrants, and I have a reference angle. The reference angle is right here. My choices of quadrants I'm not going to highlight yet because I have to kind of pare that down. Finally, I'm going to go ahead and state, since you don't actually have to write out this sentence every single time, I'm just writing this for your benefit. Since the cosine of the real theta is equal to a negative root 3 over 2, we need a quadrant where cosine is negative. Now, of these two quadrants that we only have choices of, quadrants 1 and 2, cosine will be negative in quadrant 2. Again, trig is just about quadrants and reference angles, pretty much. So we have a quadrant 2 angle with a reference angle of pi over 6. We are ready to go. I'll just draw in off to the side here an angle that terminates in quadrant 2 and has a reference angle of pi over 6, and that angle would be 5 pi over 6. So therefore, the inverse cosine of negative root 3 over 2 of a negative, sorry, that was supposed to be a negative, root 3 over 2 is equal to a 5 pi over 6. Double check that the output, the angle output there, is actually within this inequality. 5 pi over 6 is definitely between 0 and pi, which is 6 pi over 6. 5 pi over 6 is within that interval. So there you go. Again, 2 examples in a row showcasing the same steps. Now we get to an example with a ratio that is not one of our special right triangle ratios. Instead, this is a quadrantal ratio. So I will go ahead and say that this is some angle right there. And I know the restrictions on the arc cos, or the inverse cosine, is that my angles have to be between 0 and pi. All right. In other words, you're dealing with either a quadrant 1 or a quadrant 2 angle. So those are my choices of quadrants. That's my quadrant. I'll just use Q for quadrant there. That way it's just shorthand. Very nice. Quadrant. There we go. Now, since this ratio is not like a half or a √3/2 or something like that, like from a special triangle, since it's a 1, a -1, or a 0, this I know is going to be a quadrantal angle. And what do I mean by a quadrantal angle? Well, first of all, let me write that since part. So since 1, that looks like I, but it's the number 1, is not a special ratio from a right triangle, let's draw the graph of the cosine. And so drawing the graph of the cosine here, the following. Here's the cosine curve from 0 to 2 pi. And, oops, did not mean to erase my x-axis, just that part. And we know here's the special angle pi, and here's the special angle pi/2, and so on and so forth. And you could see what we're looking for is we need the cosine of some angle, theta, to be 1. Well, if you take a look at all the angles between 0 and pi, which is exactly what the cosine inverse will return, angles between 0 and pi. Darn it, I meant to erase the highlighter and fix it, but it's because I'm so zoomed in. Anyhow, there we go. I'll do that, and then I'll draw in my x-axis. Yay, there we go. Okay, so since our angles that the cosine inverse are going to return is between 0 and pi, we know that that highlighted region is the only region of candidates for angles that I can plug in. I need an angle to plug in, so the output is 1. And if you take a look at that interval, have I plugged in 0, I get an output of 1 for the cosine. So that means the angle must have been the angle 0. So I know that the arc cos, or the cosine inverse of 1, must be 0. That's the radian angle I would plug into the cosine to get an output of 1 according to its graph. So often when you're dealing with quadrantal angles, they're a little bit faster because all you have to do is really draw out the trig function. And this is another reason why knowing the trig graphs is critically important as we move forward. Something I do want to mention as I was going through this problem is that I stated in our first page in this step right here that, actually it would be in this step right here, if the argument of the inverse trigonometric function is a -1, 1, or 0, then the angle is a quadrantal angle. That's not necessarily true in two cases. If you're dealing with the cotangent inverse or the tangent inverse, because turns out the tangent of pi/4 is equal to 1. And so the tan inverse of 1 is actually pi/4. And so that's an exception to this rule. The same thing, actually, cotangent inverse of 1 is also pi/4. So that's a little bit of a specialty case there. But again, not that big of a deal. Once you get used to inverse trig functions, you'll be able to barrel through that. That's not a huge issue. Speaking of the tangent inverse, here we go. Let's evaluate this expression, again, without using a calculator. So I happen to know this is going to return an angle. I also know the angle that gets returned by the tan inverse is between -pi/2 and +pi/2. Again, that's from the previous video. We talked about all the quadrants and angles that can be returned by an inverse trig function. That's my quadrant step. Let me go ahead and list out the quadrants too. It's quadrants 1 and 4. All right, there we go. And now let's do the reference angle step. In this case, this is a special trig ratio. We just need theta hat, a reference angle, such that tangent of theta hat, let me write that in, tangent of theta hat is equal to a positive √3. Again, I don't really concern myself with the negativity of this until I lock down the quadrant. That's an important conversation as we move forward. So let's go ahead and draw out our special triangle here. We have two of them. I'm just not picking on the 45, 45, 90 one. 1, 2, and a root 3. And remember, tangent is opposite over adjacent. Opposite, root 3. Adjacent, 1. Root 3 over 1. So obviously I would like theta hat, my reference angle, to be pi over 3. So this implies theta hat will be pi over 3. I now have a reference angle. And now I'm not going to write out those words since or anything like that. I will just point at this negative here. In fact, maybe I'll do it this way. I'll point quadrant 4 at that negative, because the reality is between quadrants 1 and quadrants 4, where is the tangent negative? Yeah, it's negative in quadrant 4. So quadrant 4 is going to be my winner. So we have a reference angle and a quadrant. Now here is an interesting piece. This is why I tell my students, please make sure you write out that inequality. Because I will have some students that say, oh, quadrant 4, great. That means theta has to be, let's see, a reference angle of 5 pi over 3, or sorry, pi over 3, means that if that is my reference angle of pi over 3, it means my actual angle is 5 pi over 3. You would be wrong if you said the tangent inverse was equal to 5 pi over 3. It's because the tangent inverse can't return an angle beyond pi over 2. And 5 pi over 3 is well beyond pi over 2. So, how do you rectify that situation? And the answer is fairly easy. You want to go down into quadrant 4 via a reference angle of pi over 3. So your actual angle is a negative pi over 3. That's simple. So theta is negative pi over 3. That is the tangent inverse of a negative root 3 is a negative pi over 3. Now, I don't recommend you memorizing all the inverse trigonometric values, because that would be a waste of your time. Instead, you should get used to working with this method, right? Your tan inverse or your trig inverse function is equal to an angle. Where is that angle restricted to be between? Well, negative pi over 2 to pi over 2. So that's quadrants 1 and 4. What is the reference angle for that specific inverse trig function? Find that. And then use the quadrants and the reference angles to lock down the actual angle. And now we get into a ratio that is neither a special ratio nor is it a quadrantal ratio. This is something which will require a calculator. But I still kind of tackle it the same way. This is going to be some angle, where the angle is between negative pi over 2 and positive pi over 2. And in fact, let me read the instructions, because they might require, yep, and they do, they require degrees in this answer. So you do have to pay attention to that. So I'm going to go ahead and trade these radian angles out for degree angles. So negative 90 degrees to positive 90 degrees. All right, great. So we now know, oh, and that's, by the way, quadrants 1 or 4. Now, you don't have to do all these steps in the order that I have written them in that how-to. I can immediately see that because this ratio is positive, we're going to deal with quadrant 1. So because it's positive, sine is positive in quadrant 1. So there I already know my quadrant. My quadrant step is completely done. Now let's find the reference angle. Well, the fact is that when you're in quadrant 1, your reference angle is actually going to be your true angle as well. Again, if you find your reference angle is 10 degrees and you know your answer's in quadrant 1, then your actual angle is 10 degrees. So the reference angle and real angle are going to be the same here because you're in quadrant 1. But I'll treat it, just to showcase how I do this, I'll treat this as if it's a problem where the reference angle is not, or the real angle is not in quadrant 1, just so you can see the thought process. So to find the reference angle, because of the fact that this is not a special triangle, I'm going to go ahead and find the reference angle by grabbing a calculator and evaluating the sine inverse of not what they handed me, but the absolute value of what they've handed me. That's how you get a reference angle. Now, what they've handed me is already positive, so technically I don't need the absolute value. And so when I grab a calculator, I'm not going to bother with putting in an absolute value. But this is just an important note to make. When you find reference angles, just like we did actually in all the previous problems, when we found the reference angles for something like tan inverse of negative root 3, I looked at the root 3, not negative root 3. I looked at root 3. And the example, not prior to that, but one back, this example right here with the sine inverse of root 3 over 2, I looked at root 3 over 2, which is the absolute value of root 3 over 2, to find my reference angle. When I worked with the cosine, the arc cos of negative root 3 over 2, again, my reference angle, when I went to look for it, I looked for the reference angle associated with positive root 3 over 2. So again, every single step of the way, I'm not worried about the negativity of the ratio until I'm trying to find the quadrant. That's the only reason why that negativity of the ratio exists, is to help me find the quadrant, not the reference angle. So going back to this example, we now need to compute this. So we're going to go over to Desmos, and because we want our answer in degrees, I'm going to make sure that we're in degree mode when we do this. Okay, so here we are in Desmos, and you could just type in the arc sine of, and it was 0.9983. And you can see right there, 86, and we're asked to round to the nearest tenth of a degree, so 86.7 degrees. There you go. So that is not too bad. That's our reference angle. And because we're in quadrant 1 with a reference angle of 86.7 degrees, the actual angle is 86.7 degrees. So the sine inverse of 0.9983 is approximately 86.7 degrees. All right, that doesn't seem too bad when you grab a calculator. But there are some potential pitfalls, and here is one of them. Evaluate the inverse trigonometric function to the nearest tenth of a degree. So we're still working in degrees here. And I'll go ahead and make the mention that secant inverse is going to return an angle. Now this example is really for my pre-calculus students, because my trig students are likely not to see a secant inverse. However, when you reach pre-cal, you do have to kind of get used to this. And definitely in calculus, you do have to kind of get used to the the range restrictions on a secant inverse. So secant inverse returns an angle, right? And that angle, according to the definition, this squirrely looking weirdness of a definition, the secant inverse is this guy right at the bottom right there. And it returns angles between 0 and pi over 2 and pi and 3 pi over 2. So quadrants 1 and 3. And of course, we are dealing with degrees, so it's between 0 and 90 degrees, or 180 degrees and 270 degrees. Let me write all that stuff in there. And this is, by the way, our quadrant step. Let me put a little Q there. And that is quadrant 1 or 3. Depending on whether this is a negative ratio or a positive ratio. The fact is, it's a negative ratio. We know that all trig functions are positive in quadrant 1, so this must return an angle in quadrant 3 because we have a negative ratio, so our quadrant must be 3. Again, I only deal with that negativity on that ratio when I'm determining quadrants. So I know now that whatever answer we get, it's gotta be an angle in quadrant 3. And it has to be between 180 degrees and 270 degrees. Now let's find the reference angle. And here is where it gets tricky. If you thought that last piece was tricky, this is where it really does get tricky. The sad fact is that there is not a calculator that has a secant inverse button on it. They have cosine inverse buttons, but not secant inverse buttons. So we are going to have to rewrite this in terms of cosine. Now, I do want to mention off to the side, because this is critically important, I'll see students make this mistake all the time. The secant inverse of, in this case, negative 1.1123 is not 1 over the cosine inverse of negative 1.1123. It's just not the same thing. So you cannot do that. The reciprocal relationships between the trig functions are only between the trig functions. So if these were not inverses, it would be sort of true, even though technically speaking, you cannot plug a negative. Well, no, yeah, this would be true if it was not an inverse function. But inverse functions, the secant inverse is not the reciprocal of the cosine inverse. So unfortunately, that's just not the case. So let go of that. You can only do the reciprocal stuff when they're the base trig functions, not the inverse trig functions. So that being stated, how do you work your way out of the secant inverse? Well, you trade it out for the alternate form. Theta equals secant inverse of a negative 1.1123 implies that the secant of theta, is equal to a negative 1.1123. And then I'm going to trade out that secant. Now that I have it as a trig function, not an inverse trig function, but a trig function, I'm now going to trade that out for a 1 over the cosine. Now I can do that. I couldn't do it before. And you will see a significant difference between the secant inverse of negative 1.1123 and what we thought it should be, which is a 1 over cosine inverse. It's not going to be that. Now take the reciprocal of both sides to isolate the cosine. So I'm going to write the implication signs here. This implies the cosine of theta is equal to a negative 1 over 1.1123. And now I can actually find my reference angle here by noting this will imply theta hat, I should say, is equal to the cosine inverse of, remember when I find reference angles, I do not care about the negativity of this. When you're finding reference angles using a calculator, do not worry about that negativity. It'll be the absolute value of that negative 1 over 1.1123, or in other words, it'll just be the cosine inverse of 1 over 1.1123. So just letting you know, this whole entire step is to find the reference angle. To find the reference angle for one of the reciprocal functions, secant inverse, cosecant inverse, cotangent inverse, you will have to rewrite it in trigonometric form, not inverse trig form, and then trade that trig function out for its reciprocal function, then solve for that reciprocal function, and then say, well, if cosine of theta is equal to that, then the reference angle should be cosine inverse of the absolute value of that ratio. And now we can go grab a calculator. So I'm going to go grab a calculator, or I'll hop over to my calculator, and I'll type in here arc cos of 1, oops, that was supposed to be 1 over 1.1123. You can see that's a 25.96, which is 26.0. So roughly 26.0 degrees. Now remember, this is my reference angle, not my actual angle. That is my reference angle. It may seem like we've done a lot of work here, but you can see it's very few steps that we've done. Now that we know the quadrant and the reference angle, I could say the actual angle that secant inverse is going to return, secant inverse of negative 1.1123 is going to be approximately, well, we rotate into all the way around into quadrant 3. We have this reference angle of 26 degrees. So we went 180 plus an additional 26, we are actually 206 degrees. So roughly 206.0 degrees. And that is the secant inverse of a negative 1.1123. This is a great style of question to ask on an exam because there's no way you can use a calculator to find that. You have to actually showcase your knowledge of working with quadrants and reference angles and your actual ability to remember that secant inverse returns in quadrants 1 and 3. Kind of an oddball function, honestly. Now let's start working with curveballs here. This is where we start really trying to ferret out what's the difference between being asked for the inverse of a trig function versus, hey, what angle would you plug into a trig function to get this output? Notice here that this is not an inverse trig function. What does that mean? It means theta is unrestricted other than domain issues. The cotangent does have domain issues at 0 and pi and 2 pi and all that stuff, but otherwise there's no real domain restrictions other than the natural domain restrictions for the cotangent. And I've written that right there. Now let's read the problem. Find theta if it's an acute angle. So they knew, whoever wrote this problem, me, knew that there are an infinite amount of answers to this. If I were to graph the cotangent of theta and set it equal to 1.222, you'd get the following. There's my cotangent graph, really, and the blue line is 1.222. Notice it hits that cotangent an infinite number of times. So to keep you from giving me an infinite number of answers, I've specifically stated I want theta to be an acute angle. That is, I want theta to be between 0 and 90 degrees. So theta here, they being me, have restricted you to answering between 0 and 90 degrees just from the first sentence. And then we're just going to round the answer to the nearest tenth of a degree. Well, how are you going to find that angle? We'll go ahead and grab that, and we're going to basically say that if cotangent of theta is 1.2222, we're going to use the definition of the inverse trig functions to say, therefore, theta must be the cotangent inverse of 1.2222. However, we know that we do not have a cotangent inverse button on our calculator, because if you didn't know that, you only have sine inverse, cosine inverse, and tangent inverse, the top three. You don't have any of the other arc functions or inverse trig functions on your calculator, nor does Desmos. So how do you rectify this situation? Well, you go back to the drawing board and rewrite your original problem in terms of tangent. We want the cotangent of theta to be 1.222, so we want 1 over the tangent of theta to be that 1.2222. If you take the reciprocal of both sides, you'll get that you want the tangent of theta to be 1 over 1.2222. And now we can say, okay, if tangent of theta is equal to that number, which is positive, by the way, then I know that theta will be the tangent inverse of 1 over 1.2222. Technically, it's theta hat. And then I will reference back to what they told me in the beginning. Oh, they want my angle between 0 and 90 degrees. So remember, our reference angle is going to be between 0 and 90 degrees. Our reference angle is actually going to equal our actual angle in the end. But let's go ahead and just grab a calculator really quickly. I'm going to hop over to Desmos here. I'll do the arc tan of 1 over 1.2222, and you get 39.3 degrees. There you go. Now remember, that's our reference angle, but then we find that because we're being asked for an angle between 0 and 90 degrees, the reference angle is going to be the actual angle. So I'll go ahead and write that in here. So the solution to cotangent of theta is equal to 1.2222 on the interval 0 to 90 degrees is roughly equal to 39.3 degrees. So that's not too terrible. I mean, it could be worse. As a final example, let's go ahead and take a look at this guy right here. Use a calculator to find theta to the nearest tenth of a degree. So a few things I need to note here. 1, we need degrees. All right. 2, we're given 3 separate conditions. Our 3 separate conditions are the following. Theta is between 0 and 360 degrees. So I have a full rotation to deal with here. There might be multiple answers. Then the second condition is that the sine of theta is equal to a negative 0.1291. Okay, that's my second condition. And by the way, the fact that it is a negative number means that theta will either be in quadrants 3 or quadrants 4. So without reading the rest of the problem, I know that's the case. But then the final condition is that they restrict theta to be an angle terminating in quadrant 3. So I can get rid of the quadrant 4 possibility. So now I know I'm locked down to quadrant 3. And to find the reference angle, you must work with reference angles here. The reference angle is going to be the sine inverse of the absolute value of negative 0.1291. Again, every time that I work with finding the reference angle, I do it not for that negative ratio, but for the positive version of that ratio, always. So my reference angle is going to be the sine inverse of 0.1291. Again, that'll just be my reference angle. So let me go ahead and find out what the arcsine of 0.1291 is. So we type in arcsine of 0.1291. We get 7.4 degrees. Very roughly 7.4 degrees here. Now, that's not my actual angle. That's the reference angle. I have that reference angle in this quadrant. So if you can visualize it, you have an angle rotating into quadrant 3. It's a very small reference angle of 7.4 degrees. So you've gone 180 degrees. You're adding an additional 7.4 degrees. So therefore, the actual angle that you're working with is approximately 187.4 degrees. That would be the value of the angle such that the sine of that angle would be negative 0.1291, where the angle is in quadrant 3. Now again, I just want to reiterate, we started this problem not with an inverse trig function. So this goes back to what I said a couple pages ago, or 1 page ago, that what we started with was not an inverse trig function, so theta was unrestricted. So there was no like, oh, it has to be in it has to be between negative pi over 2 and positive pi over 2. There was none of that in that conversation because, again, we weren't starting the problem with an inverse trig function. So there was no restriction on theta until they told us in this problem right here, until they told us, oh yeah, there is a restriction on theta. It's in quadrant 3 and it's between 0 and 360 degrees. So they purposefully told us to restrict the angle, but this is not a sine inverse problem by itself. We had to use the sine inverse to find a reference angle, but that was it. All right, so very critical to see that. Also, something that I fail to do very often, in fact, is things like this. Oh, what's the tan inverse of, and then I give you some value. Actually, tangent inverse is a bad one. If I give you a sine inverse of 1.1123. First of all, you would say, oh, that's some angle, but you should note, you're saying that there's a sine of some angle that's equal to 1.1123. That can't happen because the sine never reaches a value greater than 1. If you were to grab a calculator and try to compute that arc sine of 1.1123, you'll see it's undefined. And that's because the, again, sine function will not return a value greater than 1. So that's just a little side note. Your calculator will tell you if the world blows up, so that's good. But just use some logic in there too. So that pretty much does it for this video on evaluating inverse trig functions. Next video will be dedicated to evaluating compositions involving inverse trig functions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.